All right, let me just make sure the audio is working. And then we can send out the poll for today. Time is it? 11:02. Do we want to get started yet? Maybe wait like 2 minutes. We're gonna wait like 2 minutes and then we'll get started. At some point when you get a chance, can you add the link to your sessions under the peer leading sessions tab in Canvas, because I don't know about everyone else. But to join your sessions, I'd scroll all the way down your announcement, find your original announcement in the semester. Thank you for letting me know. I thought I added it already. Maybe I didn't do it for both sections. Maybe I only did it for one section. So yeah, I'll make sure I do that. I could probably just do that in a second. Okay, so today, what I want to do with all of you is kind of go over all of the general test questions. And this will be the best if everybody kind of has something to work with me. So if you have, I'm going to kind of give you guys like 2 minutes, 3 minutes to kind of work out each problem. And then if somebody wants to kind of share how they solve the problem, then that'll probably be the best way to do this. The first question that I'm going to ask is, okay, given this heap, given this unsorted, given this binary tree, I should say, binary tree. And remember, binary tree is just an array. Given this binary tree, heapify, or describe, I guess you could say, detail the steps to convert into a heap. So that's part one. And then part two, what is the time complexity of this operation? Okay, so now let's actually draw this binary tree. So I'm going to try to make this look better. So
sorry to interrupt. Are we supposed to be able to see the screen?
Oh, you're so right. Oh, my bad. See,
No,
this is why the recording that I made for you guys last time was messed up. Okay, so I'm going to draw out this binary tree. You guys can see the screen now, I'm guessing, right?
Yes.
Okay, awesome. That's going to go on that side. Okay, and then let's just move this. Okay, there we go. And there we go. Now let's actually start getting the numbers. At the top, we're going to have 5. Here, we're going to have 9. Here, we're going to have 6. And this is going to be 7. And this is going to be a max heap. Should have specified that up here, but I'll put that here. This is going to be a max heap. 5, 9, 6, 7. We're going to have 3. We're going to have 11. And we're going to have 2. So I'm going to give you guys like 2 minutes. You want to work these out and then share. I'm going to give you guys exactly 2 minutes to kind of work through part 1, and then maybe like another like 30 seconds to work out part 2. Okay, so wait, hold on. Let me just make it out. Okay, there we go. Does anybody have any solution for this problem that wants to share? Okay, so I'm just going to go ahead and kind of work this out. So the algorithm that we're trying to depict here is the Heapify algorithm. So let's just kind of write that in here. The algorithm. The Heapify algorithm is going to just let us kind of take any binary tree and convert it into whatever type of heap you want in some amount of time, which we'll talk about down here. So let's actually kind of work through the steps. So let me just come up with another one. Let me make this longer so that I can just kind of write this out. Okay, and I'm going to change this to 18 cells. So step 1, And I'm going to kind of iteratively describe the steps and then kind of write out some tiny piece of, I guess you could say, pseudocode for the rest of the steps. So step one, what's going on? Make it better. Okay. So step one, we're going to start at 2. You might ask why. We're starting at 2. And you automatically just kind of want to remember what the heap is doing. And the heap, like we said, is maintaining our heap property. What's our heap property? The child is either less than or equal to the parent, or the child is strictly greater than or equal to the parent. And that whole idea is going to keep either the min node at the top or the max node. In this case, we have the max, so the child has to be strictly less than or equal to the parent. So we're going to start at 2 and compare to 3, and then we're going to check. So in this case, we're good. So I'm going to say, I'm going to use true to kind of indicate that we are maintaining heap property. So heap property, true. Okay. Step 2. Step 2, we're going to we're going to start at 11 in order to compare to 3. Heap property, false, swap with. So right now, you're going to immediately notice, so I'm going to draw an arrow, actually. I'm going to copy this just in case it locks me out. Yeah, it's going to lock me out. But I'm just going to draw an arrow from here. That's not the kind of arrow I want. I'm going to draw an arrow. Do I have a good arrow? They don't really have that many good arrows. Okay, so I'm just going to use this. And these two are going to get swapped. So now we have 11 here and 3 moving there. Awesome. Okay. Let me get rid of this. Create a new one. Okay. So we swapped that with the parent. Then we're going to keep iterating through the rest of our list. So we're going to go to 7. So step 3. And you can think of these as iteration. Iteration. I'm going to call this an iteration. Iteration. Iteration 3, we're going to start at 7. Compare to 9. Is the heap property maintained in this case? True. Heap property is maintained. And then what we're going to do now is go to 6. So go to 6. I'm just going to kind of type this out faster. So where is it? We're on I4. I4 start at 6. Compare with somebody. Why did we start at 2 and not 6? So yeah, we'll talk about that in 1 second. Let me just finish out iteration 4. So we're going to compare 6 with 9. Heap property. Yes, sure. Okay, why do we start at 2 and not 6? It's a great question. What does this array look like in actual practice? You're going to have a 5, a 9, a 3, 6, 7, 11, and a 2. So you can think of this as going backwards through our array. and basically maintaining our heap property in that regard. There was another, I guess you could say, step here, which we didn't kind of like, which we kind of didn't really talk about, but we'll talk about it again later in this algorithm, which is kind of like, okay, so if you want to build your max heap from an unsorted binary tree, so your binary tree without any kind of like sorting, and the numbers are just in any place, so you kind of have to assume everything is already messed up. You have to start at the last child node. You have to work your way back through each layer of the tree. That's kind of the whole idea with this algorithm, is that you're going to be working your way back through the tree. And you're going to be performing swaps on your way, and those swaps are going to kind of keep your heap property maintained while you're kind of doing this little iteration. That's kind of what I'm trying to show here. So iteration 1, iteration 2, iteration 3, iteration 4. You're just going to kind of compare everything with the parent. So we could kind of detail that out. So we're going to start at last child. We're going to compare child with, so for all iterations, we're going to start at the last child. We're going to compare child with parent. If not heap property, then swap. And then there's this extra piece, right? Because if we swap, then what we have to do is actually do a little bit extra work. We didn't have to do it here because this is the last part of the tree. But if we do have a swap, we have to check all the children that we swapped the original node with. So that's kind of why we didn't have to do it here. This doesn't have children. But if it does have children, is swap and new, actually I could write that into here. If swap, while I guess you could say, and the children, new child. So I should while we have children, then what we want to do is kind of say, okay, if not heap property, I'm going to say while children of new child C, for all children of new child, I guess you could say. So I'm going to, for all C, while C for all of children. Really what we're doing is just taking all the children of our new node. So in this case, we'd put 3 here, and then we'd check all of 3's new children. And if we find not heap property, then what we're going to do is perform another swap. And really what this is saying is if at any time you have a swap, you have to kind of iteratively check that swapping index's children. And you're going to do this until you have no more children. And that's kind of what this is. While C for all children of new child. So if your new child has any children, you're going to check to make sure that the heap property is maintained. And if it's not, then you're going to swap it. And then you're going to restart here. So you're going to go back to if swap while, and you're going to check those children. You're going to say, okay, if not heap property, swap. This is kind of like the more pseudocode way to look at it. If we actually want to like deduce this in like terms of like iterations, like how does it actually work here? So iteration 3, we could just finish this out real quick. So I5, we're going to start at 3, no, which is now 11, because of the swap. Iteration 5 is 11, compare, and we could see heap property is false. So I'm going to swap. And then in this case, we're going to, I guess you could say, let me just copy all of this, because I'm gonna have to do that. And then this 11 is gonna bubble up, and this 5 is gonna bubble down. So let me draw that in. 5 is coming down, 11 is coming up. So now we have 11 up there. And then here, let me just delete this again. And put this text back in here. So you can see now we're swapping it. So now check 5 children. Heap property? Is the heap property maintained here? If we have 5 here, and we have 3 here, it's 5 greater than 3? Yes. It's 5 greater than 2? Yes. Okay. Check 5 children. Oh, I messed this up. I clicked out. Let's delete this again. This is like my worst. This is like what I don't like about Paint. Super helpful, except in these cases. Compare, swap, and then check 5 children. E property. Yes, that's true. Keep that going. Okay, so that was iteration 5. So now I6. I6 would be this 9. Trying to think. So we had this bubble up, we had this bubble up, this 5 kind of moved down here, and then this 9 is right here. So we have a 5, we have 11, we have a 9. And you could see already that the heap is already sorted. You're gonna kind of iterate through again. So 9 heap property through, and then I7 heap property true. So you could already see that when you have, I guess you could say, this like, I guess you could say like, when you have this bubbling effect, a lot of the times you end up sorting it before you're even done. But you're definitely going to sort within some number of iterations. How many iterations do we have exactly? Well, you could have at most, I guess you could say, at most, you're going to have n plus some extra number of iterations. The worst case would be, I guess, well, hold on. Let me ask a poll. I feel like that's a good question. Can we analyze what the worst case of actually heapifying an array would be? Let me ask that. So let's do a word cloud, and this will be your attendance for today. We're gonna record names. So what is the worst case of heapify? I'll let you guys answer that. We have a couple O log n's. I should have specified. So okay. this function is called heapify in like a lot of different programming languages. This is not algorithm. I was kind of more asking what's like the time complexity. Let me restart this poll. Because I feel like this right here is probably confusing a lot of you. The algorithm is actually not heapify. The algorithm is something else. Algorithm. It's just build max heap. That's, I guess you could say, the name of the algorithm. The technical name. For me, I use this in Python whenever I use it. And in Python, the algorithm is called heapify. So the idea is you're taking some sort of array or some sort of like linear data structure and converting it into a max heap or a min heap, depending on whatever it is that you're building. But yeah, that was one subtle, I guess you could say, incorrect thing inside of that. So let me actually go back and ask this question. So what is the worst case scenario for this algorithm? And instead of actually giving me times, you can give me a time complexity. I'm completely okay with that. But if you want to even tell me, like, describe what the array would look like. What is the array going to look like in that case? A lot of people are thinking log n. A lot of people are thinking oven. Max heap. So this is actually oven. It's not log. A single operation is log. I guess you could say. So if I was going to heapify any random index, it would be log or arithmetic. But to actually apply it to this entire array, you can see we had 7 iterations. The idea is that as you're doing this, you could already kind of see you're going to have less and less swaps because you're kind of, I guess you could say, because of the way the heap works, if you apply this operation to the bottom, you're going to notice that you're going to have less and less swaps as you go up because those swaps are already going to take care of themselves. And you actually decrease the number of swaps that you have logarithmically because of the way this heap is structured. And then you end up actually with O of n, which is pretty cool because you could think of this as, well, how do you actually use this to sort? Well, I could have an array, like an empty array here, with all of my empty slots, the same numbers here. And then I could just kind of pop off of here each time. And that's going to be log of however many nodes are in this list. So you could think of it as being bounded by O of n log n. And the reason for that is because this operation right here is O of n. So it's an O of n operation. So let's kind of write this out. So heap sort. It's actually my favorite sorting algorithm because of how you're kind of using the, I guess you could say, the structure of this, which it's kind of like one of those things where it's like, oh, it just happens to work out to be nice like that. Somebody had a chat. I'll tell you this, there's so many different names. You kind of just have to understand what the algorithms are doing. And then if one person calls it up heap, another person calls it build max heap. In Python, they call it heapify, right? you're going to have a bunch of different names. Just understand that they're all kind of talking about the same thing. It's kind of confusing. But I mean, you'll see it enough and you're going to get used to it. I know you might not feel like you'll get used to it, but you'll get used to it. Don't worry. So we have this O of n for the, I guess you could say, heapify operation. So I'm going to actually try to space this out a little better of what is going on. Okay. It's like my keyboard broke. What is going on with my keyboard? Jesus. We need a keyboard. This one's like taking the beating. Am I just not able to type? Hold on. No, I could type. But I can't type here. So let me copy this. Let me get out of there. And let me start over. Ah. Okay, so we had O of n for the heapify operation. It's because I pressed tab. And now it won't let me do it again. Okay, I'm just going to stop. So we have O of n for the heapify operation plus log n for removal. And then we'd be doing the removal, I guess you could say, n times. And it's really going to be log I. So log I for an n time removal. For I, and then there's going to be this weird summation from I is equal to 1 to n, if that makes sense. So let me kind of expand this more. You might be asking, what am I trying to say here? I'm going to draw this out a little bit more. So this actually becomes the expression, and let me just draw this out in terms of like O of n plus n times the summation of I equals 1 up to n log I. And you might be thinking, why log I? Really what we're doing is we're starting at n and we're going all the way down to 1. But in reality, what we're doing is essentially pulling each one of these out. What is that going to look like? Well, every time we pull one out, we're going to have in, I guess you could say, in one, we're going to remove 1, but now we have like n minus 1 nodes. So it's going to be log n minus 1, and then we're going to pull another one out, and then it's going to be log n minus 2, log n minus 3, all the way, so on and so on, all the way until we get to the log of 1, which is just 1. And the idea with that is, if you have something that looks like this becomes, I guess you could say, just, it's not this n. I take that back. This n is actually in there. I was just kind of demonstrating this. What this becomes is we're doing something n times, and with this logarithmic property attached to it. So this becomes this n log I. And then I could get rid of this. But this I, like I said, it was in this kind of like loop control variable. But we could also say that n log I, where I is about n over 2, because that's kind of like the average. This n log n over 2 is really just the same thing as n log n. And that just kind of goes to like algebra, right? When I ask time complexity, right? What am I saying? I'm saying that this is, I guess you could say, this is less than the thing that I actually care about, right? N log n. This is what I care about. This is the actual, I guess you could say, runtime of my heap sort algorithm, plus this O of n operation. But this kind of cancels out because, like I said, this doesn't really affect this piece right here. And this is the piece that's going to increase the running time of this algorithm. The reason for that is because you have this n already inside of this piece right here, and also this log n over 2, right? That's going to automatically increase the running time of this algorithm because you're taking one thing that's in terms of n and one thing that's in terms of log of n, and you're multiplying them together, right? That goes back to that whole idea that I put up for the last exam with that whole, I guess, also the answer to this one was just O of n. But that goes back to the whole time complexity thing. And one of the things that all of you should know going into this second exam is that the time complexity doesn't actually go away. She's going to ask you a whole bunch of questions about time complexity. So similar to this, she's not going to ask you to show this. This is just for you guys to kind of understand intuitively why this is O of n log n. She'll probably only ask you to that extent, right? Just fill this in. Or just fill in like, what is the, knowing this, what is the, she might even say, well, knowing this, what is the runtime algorithm, what is the runtime complexity of heap sort? She might not even tell you what heap sort is. She might, because you might not know what heap sort is. I don't know if she went over that with you guys in class, but she might tell you what heap sort like does. Heap sort just pulls the node from the top of the heap. It just continuously pops one from the top and puts it into an array like this in a sorted way. And then what is the runtime complexity of that? That would be O of n log n. And like I said, why is it O of n log n? It's because every single time you pop something, you're going to end up with an average case of n log n over 2, right? With this n over 2 inside of this log, just because of the like averaging, right? You're going to have 1 and then you're going to have n. What's the midpoint? N over 2. It's really n over 2 plus 1 is the midpoint. I'm just going to cancel out that plus 1. The plus 1 you could clearly see isn't going to really affect anything. And this over 2 doesn't affect anything either because, like I said, n can be 1,000. That divided by 2 doesn't really do much. And it could just, n can go into infinity. And that division by 2 is always going to be constant. You can't really stop the growth of a constant. You can't really stop the growth of a variable that can grow to infinity with a constant divider by 2. That just doesn't make sense. But yeah, this is a really important question to know for the exam because I know she asked a very similar question to this when I took her class. So definitely, if any of this is confusing, make sure to kind of review your heaps. She really likes heaps. She also really likes trees. And that's going to bring us to our next question. For question 2, I'm going to give you the post order of a tree. So kind of like the, I guess you could say, I'm going to give you the post order print. Hold on, what happened? My keyboard disconnects all the time. Why is that keep happening? I'm so sorry. Post order of a tree. Given the post order of a tree and the roots, draw the tree. I think it's actually so when I actually took her class, she gave us the post order and the pre-order. So I'm going to actually, do I want to do that or do I just want to give you the root? I'm trying to think. Let me come up with some tree. Ba-ba. And it'll be something really cheesy. Given the post order of a tree and the root of the tree, draw the tree. So here's the post order traversal. It's going to be G, H, D, E. Give me 1 second. G, H, D. L, B, A, C. No. I, J, F. Okay. Given the post order of a tree and the root, draw the tree. So I'm going to tell you right now, the root is going to be A. This is the question she's going to ask you almost identically. Did you ever answer this? Okay, my bad. So after each swap, you need to check the children to make sure that the heap property is still maintained. Did I understand that correctly? Yes. Every time you swap something in a binary tree like we have here, you're at risk of kind of having something from the top that's out of place, being thrown into another place that's also out of place. Kind of like if instead of here, let's say we had, forget we did this swap here. Let's just assume that we moved 9 here and 5 here. 5 would still be out of place, in which case we'd have to move 5 down to one of these places. You would probably do it to the first child. You'd have some sort of way to get the children. It doesn't really matter which child you put there, but then you'd swap them. And then you'd have then you'd run into another issue where this is also larger than this. So then you'd swap these two again. Essentially, what I'm trying to get at is you have to make sure that every time you swap something that you didn't mess up the heap property. I thought she said she won't be drawing trees. That we won't be drawing trees. You might be right now that I think about it. Because I just realized your exam is online. She had a question on here though. That's a very What?
I think originally she was gonna do it on like certain questions on paper. That's why she had the practice upload for like, for us to upload the drawings. But last
Yeah.
class she mentioned that she's actually not doing the drawings and uploads, so it's just gonna be all like on the computer. And I think she mentioned the drawing tree questions are gonna be swapped with she gives you a tree and she like tells you to give out the output, or she gives you the post order and the in order, or post order, pre-order, whatever, and then we have to like give the other order of it that's not
Okay.
provided.
Okay. Yeah. Okay. So let me change this question then. Because I guess, yeah, because your exam is going to be online, she's definitely not going to ask you to actually do something like that. So let's do this. Given the post order of a tree and the pre order of a tree, give the in order. Given the post order of a tree and the pre order. Give the in order. Okay. Okay, so now let's do pre-order. So this is post-order. This is going to be pre-order. So pre-order is going to be A. A, B, D, G, H, C, E, F, I, J. Okay. Okay. Now I clearly know the in order because I'm looking at the tree right now. But assuming that I'm not looking at the tree, I'm gonna actually put this tree away. And I kind of let me just make sure that this is right. A, B, D, G, H. There's an L right here. Because I kind of visually modified the tree. C, E, F, I, J, G, H, D, L, E, E, I, J, F, C, A. Awesome. Okay. So I don't understand how we're supposed to do this without having Scratch to draw the tree. That's a good question. How would you actually approach this? Well, you already know. Well, let's actually kind of draw out the tree. Um, you could draw out the tree in kind of like a, I guess you could say, yeah. I feel like it's not easier. She gave us the same question on paper. Actually, she gave us this question on how to draw the tree, and give the in order. Or she gave us the tree and asked us to give the in order, the post order, and the pre order. But let's just do the reverse for now. How do you actually approach a problem like this? I know the root is A. Why do I know the root is A? Because the pre order says it's A. But also the whole idea with that is, well, I kind of said that the root was A before. Then if I know that A is the root, then I know that here C must be directly to the right of A. How do I know that C is directly to the right of A? Well, because of this. If C wasn't directly to the right of A, then I wouldn't have all of this, I guess you could say. Hold on. I can't even do. Can I type still? I could type, but I can't type into here. And delete. I can't even delete. Okay, whatever. I am going to try to not draw this out, but just kind of write things down. So you have A. A we said is the root, right? Because pre-order, post-order. Okay. So from A, you can deduce that C is somewhere off in the right subtree, and that G must be somewhere off in the left subtree. So then it becomes a matter of, well, okay, what is pre-order? Pre-order is going to look something like this. A, B, plus, like, we're going to essentially, how do you say? I think maybe it would be better if we just have the algorithms here written out. So post order of a node is you print, so it's post order node to the left, post order node to the right, post, and then print n. Pre-order of n is going to be print n print n to the left, print n to the right. Okay, so let's kind of look at what this means for us. The pre-order means that we're going to collapse our n's left node first. So this must be the most leftist node in the entire tree. So essentially, where's my pen? Where's my pen? Okay, so the most left node is going to be G. From there, let's actually figure out how many layers we have in this tree. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 layers, 11 nodes. So what's actually the max depth of this tree? D would be, I think it would be 3. Would it be 3? It would be 3. So D would equal 3. Let me just confirm. D would be 3. Okay, awesome. Now we know the depth of this tree. Let's kind of try to use that to work backwards. Okay, so if we post order and get A and C, so if this is post order, right, that means that our root printed last, which means that second to last is the rightmost node from our root. So we're going to say this is level 3. I don't know how you, to be honest, this is going to be a hard question to do on paper. I don't think she'll give you this. She'll probably give you a tree and ask for the post, pre, and in order, but let's just continue with this example because it's a little difficult. So at level 0, we're going to have A. Oh, that was a bad A. Let me redo that. We're going to have A. All the way to the left, we're going to have G. Directly to the right of A, we're going to have C. And directly to that right, we're going to have an F. Or something along those lines. Let's kind of mark that. So we know we have a C and we know we have an F somewhere in this subtree over here. Remember, this just has to be an accurate tree. It doesn't have to be the exact tree. Because as long as the post order and the pre-order work, you can kind of come up with some number of configurations that do the same thing. So G we said is all the way over here, which means that H, right? H is going to be somewhere over here. It would be wrong of me to give you a tree without a balanced, I guess you could say, number. So each internal node must have at least 2 leaf nodes. That would just be wrong of me not to do. G, H, so G, we could say H, right? That's the right, which means that D would have to be here. And then G here. So if we look at the pre-order, well, what's pre-order? Print yourself, B, and D. So that means that the father of D must be B. Because if you look at this, right, A has to go to B, and then B has to go to D, and then D has to go to G, and then H, right? Because left node, right node. Okay. And then what's after that? L. So we have an L somewhere in here. I'm not going to really draw that yet until I look at this post order. So if the post order, well, it's going left, right, and then U. So let's post order this for a second. So post order, we have G, H, D, L, so L, E, and then some other E. So because this L is in between B and D, that means it has to be here. There's no alternatives there. And the reason for that is because we saw L here, right? In the pre-order. The pre-order was print A, print the left tree. So B, then D, and then G, and then H, and then L. And then we're going to come back up to here. So that means all the way H, L, C, which makes sense because we're already printed here and now we're going into the right subtree. C, and then E is somewhere. Where would E be? Well, let's kind of look back here. We have F here. So these two Fs are kind of lining up too. That's interesting. Post order of this tree on this side has A here. And there's a J. So post order is left and then right. So the post order has taken us all the way here back to, I guess you could say, where's L? So B, we already have that. So E. So the most left node in this tree is E, but I don't know where it is yet. And then I is another most left node. This tree is a little harder to build out because of this. J, well, let's match up J. J, the pre-order, is most likely a child node, probably all the way into this corner. So I'm just going to kind of write that. So J is most likely the child node all the way into that corner. Okay. And then I, where would I go? I is either, I has to be here actually. Now that I think about it, because I kind of already told you guys that you're not allowed to have a tree without two nodes here. So C, F. Well, if the pre-order has F there, then F has to be here, just based on kind of what we had here. So C, F, I, J. We had J, we had I, and F, right? We had here, right, A, C, F, right? We said this whole thing is kind of like the right branches. And then if we look back, I, E, which tells me something about E. E has to be right here. Why does E have to be there? Because these branches are going to have to build up, right? We're going to go rightmost subtree. So J, where is it? J, F, C. That's the rightmost subtree from A. And then if we go backwards from there, we're going to get I and then E. I and E, right? It's going to go left, all the way left first. And then it'll let you start going right. Which one was that? That was post order. So we're going to go all the way left as we can. And then we're going to go all the way right, left, right. Oh, we got to J. Then we come back and we print ourself. Then we come back and print ourself. Then we come back and print ourself. And that's the root. So you can see, I mean, it's not easy to build out this tree. But it's definitely possible. We're going to have another session tomorrow morning. I am having another session tomorrow morning. Well, we'll do more stuff with trees. But now that we have the tree, what's the in order? We're a little over time, but that's okay. We could probably get the in order really quickly. I'm going to leave this up. Does everybody understand how we got the tree? Let me just, let's take a poll real quick. Because the process of getting the tree is more of just kind of like, it's like a puzzle. You kind of have to figure out where the pieces are going, and make sure that they obey these rules. These are the rules that these post orders live by, and you could have some weirder configuration, no doubt about that. You could have these two have their own subtrees and these two have their own subtrees, and you could still fit in the puzzles based on this. It's just going to take the more nodes that there are. She'll probably give you something that looks like this if she was going to actually do anything like that. I don't, like I said, I don't think she's going to have a question like this. I think she'll probably give you all, what's it called? She'll give you the tree and then ask for all of them. Meaning you have to remember these rules, but just kind of reconstructing this tree from the post and pre-order is also kind of important just because of, I guess you could say, the like understanding how the puzzle pieces fit into each other. Do you need both the post and pre-order to find in order? You do. Because the in order is going to depend on what the tree looks like. Essentially, the post order, right? The post order might have one subtree with one node and one subtree with like all of the nodes. And you wouldn't really necessarily be able to tell. Can you write out? Yes, I can write out the post order. I just want to take a poll real quick, and this will be your last attendance. How many of us actually understood? Do we understand? Because I don't really have a good way to how to build tree from pre and post orders. And this will be your final attendance. Do we understand how to actually do that part? Like I said, you're taking these rules and you're kind of applying them. You can, like I said, if it's a binary tree, you can get the, what's it called? The depth by just taking the log of the number of nodes. And that kind of helps you figure out where each of these go. Also, with pre-order, the first thing that gets printed is the root. And with post order, the last thing that gets printed is the root. But one thing you could see is like I could take this I and j and I could throw them here. And it would still be a valid binary tree. But the pre-order and the post-order would change. We could show that too, but we have a guess for in order traversal, it looked like. So G, D, H, I'm cool with that. B, L, A, yep. E, C, I, F, J, yeah. Yeah, exactly. Let's actually write that out. So G, this doesn't like my keyboard. Get rid of that. G, D, H, B, L, A, E, C, I, F, J. I'm hesitant to say she won't ask you a question like this because of this, but it's also Korsova, and she might ask you something like this. We could kind of go over this again next time, if you want to. Next time being tomorrow morning. Kind of. So most of you seem like you either understand it completely or you kind of understand it. Like I said, this whole in order traversal, you could pull from this post order and pre order. You can't get it from one of them because, like I said, you don't necessarily know what the tree looks like. How did you get the height again? It's the height, the depth is just the log of the number. So in this tree, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The log of 11 is about 3 point something. So you know that the depth has to be 3. The log is somewhere in the middle of 3 and 4. You always round down. If it's a somewhat balanced binary tree, you always round down. If it's a balanced binary tree, then it has to be down. Exactly. Log of 11 is 2. Log of 11 base 2. So log base 10 of 11 is 1. Log base 2 of 11. Do that. That's gonna be really is just saying 2 to the third power is 8, and then you have like 3 floating ones, right? If I were to make this as balanced as possible, you'd have 3 nodes in this last layer. Right now you have 4 nodes in the last layer, just to maintain that like balanced binary tree look, to make it easier. But yeah, everybody who came today should have their attendance checked. I'm going to stop the recording here.